Hello, welcome back. The title of this lesson is called The Discovery of the Electron. So here I'm excited to teach this lesson because all of chemistry, which is what we're really studying, right? Chemical reactions and so on, really is in the domain of what is happening to the electrons that are surrounding the atoms. When we have a chemical reaction, we have the atoms rearranging and bonding in different order from the reactants to the products. And as part of that, we have electrons sometimes being transferred, sometimes being shared. So all of chemistry really boils down to what is happening with the electrons, and a great deal of the study of chemistry is learning about what an electron is and how electrons occupy the space around the atoms. And so that's where we're going, right? Here in this lesson, we're going to do a little bit of a historical treatment of how the discovery of the electron really happened, because number one, it's fascinating. Number two, it can give us some clues into the thinking behind chemical concepts that we need to consider going forward. And the other part of it is, in this class, I really want to introduce, as best I can, our modern thinking about what electrons really are and also what photons really are, which is light waves, right? Because as we get farther and farther into chemistry, you start realizing that your teachers have been lying to you as you learn early chemistry in most books and most classes. I'm going to try to lie to you as little as possible. So in the beginning, we have a model of the atom, which we're going to talk about more later, where you have the protons and the neutrons in the center, and you have the electrons which are surrounding, and we think of them as orbiting like solar system, like planets in a solar system. That's a very useful a picture to have in your mind, and of course it is the model that the early pioneers had also. That's what they thought it was electrons orbiting like planets around the sun, right? But as we discovered quantum mechanics, we now know that electrons absolutely are not and do not behave like planets going around a solar system. In all of our modern usage of chemistry, organic chemistry, synthesizing drugs and other things is absolutely dependent on our understanding what electrons are, because electrons govern chemistry, right? And so if we can better understand what the electron is, then of course we can apply that to developing modern technology. Now, the whole concept in field called quantum mechanics is basically talking about what is an electron, how does it behave. There's something called a wave function. We're going to talk about that kind of stuff much, much, much later. Here in this lesson, we're just going to go back in time before we knew anything about quantum mechanics, before we knew anything about quantum chemistry, before we even really knew the structure of the atom at all, and talk about how the electron was discovered and what we learned about that. And then in the next lesson, we'll talk about the remaining parts of the atom, the neutron and the proton. And then as we learn the chemical concepts beyond this point, knowing that these ideas were discovered in this way, we're going to modify them and change them with our current understanding. So in a few chapters down the road, you'll understand exactly what we actually think an electron is. And I'll give you a spoiler alert, it is not a little ball that goes around the atom. It does not behave like that with our current experiments and knowledge that we have about how electrons and protons really behave. All right. So in the early or the late 1800s, experiments were done with atoms to try to figure out what they were composed of. And one of the earliest experiments that really led to the discovery of the electron was called the cathode ray tube. You may have heard cathode ray tube, you may have heard the letter CRT. Maybe you haven't, it's okay if you haven't. But basically, the idea goes like this. What you do is you take a glass tube, or you can use glass, you can use quartz, which is another clear glass-like looking material. And what you do is you pump out the air and make it a partial vacuum in here. You don't want too many atoms inside of it, because what you want to do is you want to excite the gas with electricity, and the more atoms are in there, the more energy you need to excite all the atoms in there. So what you do is you pump out a good chunk of the atoms that are there. Maybe you even fill the tube with a different gas than air, because you know air is nitrogen, it's oxygen, and there's other trace gases as well. There's carbon dioxide in the air, and so on. You may have seen the neon tubes, which glow a certain color, right? The orangish, reddish glow. You could put a tube full of neon gas or argon gas. We can make different colors by putting different gases. But in the earliest experiments, we didn't put any special gases in there. We just pumped out the atmospheric gases, and just made it a low pressure tube there on the inside. All right, so inside of this really is a gas, but it's a low pressure gas. So low pressure gas, right? And then what you do is you hook up to that, you put a metal terminal, which kind of penetrates the glass, but it's still sealed, so no air can leak out, right? So it kind of penetrates that right there, and it's a piece of metal there. And you do the same thing on the other side. You penetrate the other side, so it goes through, but it's still sealed, and no air can really leak out of this area right here. And what you do is you hook this guy up to a high voltage source. Now, I'm not going to go into the details of exactly how they generated the high voltage source, or if it was alternating current or direct current or how much or whatever. All we want to say is that this was high voltage, right? And what we do then, when you have a voltage source, you always have a positive terminal and a negative terminal. Now we know, back in the day we didn't know this, but now we know that electricity is the movement or the flow of electrons in the circuit. Electrons are in the outer shells of all of the atoms, and so they can much more easily move freely. They can bounce between atoms. And so when you excite an electric current, we now know that the electrons are the thing that's moving through the wire. So there's a positive and a negative terminal involved in every circuit, involved in every battery. So in this drawing, this is the negative terminal. And over here in this drawing, this is the positive terminal. Now, the positive terminal we call the anode, and the negative terminal we call the cathode. But I want to caution you not to get too hung up with the words anode and cathode, because I'm going to tell you right now it's very confusing. Because the definitions for anode and cathode can kind of change depending on what you're doing. If you're charging a battery versus discharging a battery, are you talking about electrons flowing, or are you talking about what we call conventional current, which is positive current flowing the other way, opposite to the electron flow? Then your definitions of anode and cathode, they might not be the same depending on what you're doing. So I've labeled them in this diagram, but really all I want you to know is that this is the negative terminal. This is where the electrons come out. And here is the positive terminal, which is opposite to the negative terminal. Now what happens whenever you have a low pressure gas in here and you put a very high voltage across this is that you start to see a kind of like this wispy ghost-like looking discharge that's happening, and it just kind of lights up the interior of this tube. So we now know what's actually happening is the metal here is basically exciting the gas here, and it's releasing electrons from the material that's inside of this, and then they're being accelerated through the gas, which also glows because we now know the gas has electrons that are orbiting there. And when you excite the electrons and when the electrons fall back down, that's when things start to glow. In fact, anything you've ever seen glow, even if you put a red hot poker in a fire and you pull it out and it glows, you ever wonder why does it glow? Like, what is causing the light to happen? I mean, did the fire like store its orange energy and then release the orange? And that doesn't make any sense. That's not what's happening. The fire, when you put a poker into a fire, it is heating up the metal. And when you release it and pull it from the fire, the metal is still extremely hot. And the electrons that are in the outer layers of all of those atoms are bouncing up and down all over the place because that metal is hot. The electrons are going up into a higher energy, and when they fall back down into a lower orbit, a lower energy state, they release a photon. Most things that you see that glow, like glow-in-the-dark stickers, things like that, that's all because electrons are falling back into a lower position closer to the atom. We call that a lower energy state. And when they do that, when they fall in, they release a photon or some photons of light, which we can see. A red hot poker works like that. Glow-in-the-dark stickers work like that. And also this glowing gas works like that too, because the electricity is causing the atoms to pump up and then they come down. When they come down, they release light. Also, lasers work that way, but we do some tricks to make all the wavelengths line up perfectly, and it makes a nice pencil beam. That's what's happening in a laser. But anyway, it was very surprising to see this wispy discharge looking thing here, because what the next step here in that experiment, when they did that experiment, we do the exact same thing. So here's your terminal penetrating in here, here's your terminal penetrating in right here. And just as before, this is the negative terminal, this is the positive terminal, and of course we have a high voltage source. I'll put high voltage source like this, right? So what happens actually is if you leave this thing undisturbed, it's a nice straight line going directly across to the other terminal, completing the circuit like this, right? But actually, if you put a bar magnet on the outside of the tube like this, right, and just kind of hold it close, then what happens is the beam of particles, it actually moves. So you can actually take a magnet on the outside of this tube, and whereas before it would have continued all the way over, but you can actually make it impact the glass. You can move it around this way. If you move it over here, maybe it kind of goes farther and then it curves up. Basically, the beam of these things, which the punchline is we now know it's a beam of electrons, right? It was called a cathode rays. It was called cathode rays because you have a cathode and you have an anode, and these rays appear to emanate from the cathode, so we call them cathode rays. And it's influenced, this beam, these rays are influenced or able to be influenced by magnets on the outside of the tube, and also they later learned they're influenced by charged plates, charged electrical plates. So around a magnet is called a magnetic field. Around a charged plate is called an electric field. So basically the beam of electrons can be moved around by either an electric field or a magnetic field. So obviously that beam of cathode rays must be a beam of some sort of charged particles. And so they were named the electron, and now we know that we call it a negative 1 charge. It's a little bit arbitrary which particle is positive and which particle is negative. Like, why is the electron called negative? All we know is that protons are 1 charge and electrons are the opposite charge. And we choose that the electron is what we call the negative species. All right, now the interesting thing about this is when you do the experiment over and over again and you put different materials in for the cathode, like maybe you put the cathode here made of copper, kind of sticking in here, and then you do it again with a gold cathode, and you do it again with an aluminum, you know, whatever different kinds of conductive materials that are sticking into here, then it appears that the beam behaves the same way. The beam, the cathode ray beam, which now we know is a beam of electrons, behaves the same way. That's a really big clue because the beam appears to be exactly the same no matter what different metal we put for the actual connection point on the circuit. Then we assume that these tiny particles are emanating from the metal, and they're always the same no matter what metal you put there. So maybe the metal is comprised in some way of these small particles which are then coming off. And that's exactly what's happening. So no matter if you put gold or silver or any other conductive material, the electrons that come off, we now know electrons everything is comprised of electrons, and we now know protons and neutrons as well. So it's no surprise to us, but back in the day, it was very surprising that the beam would behave the same. So that was a big clue that whatever that beam was, whatever those particles were, those charged particles, they exist in many different metals, many different materials, okay? So then they said, well, wait a minute, maybe we can do some further experiments with this. We can generate this beam of cathode rays, and we can influence them with magnets, and we can also put charged plates and influence them with charged plates. So let's do an experiment and try to learn more and more and more about what this beam of cathode rays really is. That was the goal. Let's see if you could figure out what these things are, because maybe it's a building block of the fundamental building blocks of matter, and of course we now know that is the case. So later on, they built a similar version of this experiment. It's going to be difficult for me to draw it because I'm not a good artist, but the basic idea is as follows. So they make another tube, but this one is shaped kind of like a horn or an ear, however you want to look at it, but it's a sealed tube, right? And this is a three-dimensional thing, so it looks kind of like a, you know, an outdoor light bulb or something like that. It's a circular thing at the end, and it goes to a small point like this. And what you do is over here, what you do is you, inside of this thing, you put a connection point here to a cathode. I'll put a negative charged object right there. And then down the way a little bit over here, you create an anode right here. But what you do is you put a hole in the anode here. So what I'll call this thing is the positive terminal, the anode. Okay, and then you have a connection point to this guy right here, and you basically, I don't want to draw the rest of the circuit because I'll clutter things up, but basically you generate the electrons here, and just like they were generated off the cathode and they accelerated, because remember, we now know that opposite charges attract. So if electrons are negative, they're going to be very highly attracted to the opposite terminal. That's why these negative electrons were accelerated in a straight line all the way down to the opposite terminal. Because electrons are negative, they're attracted to the positive terminal down here. So if we generate electrons here, it'll be accelerated and to the positive terminal. But we have now put a hole in this terminal. So most of the electrons impact kind of the annular ring right there, but some of them go straight through the hole. So basically, if I could just draw the electrons kind of coming through, they go right through that hole and they go over there. Now what we do over there is we, instead of just having a tube, a glass kind of like tube over here, what we do is inside of this thing, we put a screen. So this thing is a fluorescent screen. Now, what is a fluorescent screen? I don't want to get into all the details right now, but fluorescent is when basically you can excite it to glow in the dark, essentially. When the electron beam hits the fluorescent screen, it glows. If you look at the old televisions, the old ones, not the flat panels, the old tubes, right? If you're in a dark room and you turn the screen off, you can see the screen glowing for a few seconds before it shuts down. That's because the inside of that screen has a fluorescent coating, and inside of that TV, an electron beam was coming in and painting that screen and painting the picture. So when you turn it off, it glows for just a little bit there. Now, fluorescence is a whole other animal for a whole other lesson, but we were just talking a second ago that the red hot poker in the fire is glowing because the electrons are very excited from the heat of the fire, and they're going bouncing up and down, and when they decay, they release photon, and we see that as a red glowing poker. What's happening here is when the electron hits the fluorescent material, it kicks an electron up in the electron that exists in the fluorescent screen material, and when that electron decays back down, it emits a visible light. Because you can't see the electron beam, right? You don't see invisible beam of electrons, but what you do see is when the electron hits the screen, it kicks an electron up, which then decays back down, and a photon comes out, and that's what you see. So this fluorescent screen allows you to actually visually see where the beam is impacting the screen. Right? And we can see that if you don't do anything else, this beam is going to go straight through the hole, accelerated through the positive terminal, and then it's just going to it's going to go and impact, and you're going to see a dot, like right there on the screen, essentially. But if you want to learn what these electrons are really made of, you want to play around with this beam and see if you can get it to deflect. We already said that we can get it to deflect with a magnet. So we also said verbally that we can get it to deflect with a charged plate. So what you do is you have your electrons generated, they're accelerated through here, they hit the fluorescent screen, and then just past this positive terminal, what you do on the outside here is you put a positive plate or a charged plate on the top and a charged plate on the bottom. So this could be like the negative plate, and this could be the positive plate. But you have like a separate circuit that's going on outside here just to charge this plate up. And you can change the charges on here, and when you do that, the beam is going to be bent up or down, and depending on how you orient the plates, you can get the beam to be steered. Because the beam is, we now know, a beam of negative electrons. And so it's going to be repelled from this plate, and it's going to be attracted to the positive plate. And as you adjust the relative charges, like if you flip this one back positive, you can make the beam go up and so on. And so that's how you can paint an electron beam on the inside of a TV, right? But then you go a step further and say, okay, I can bend the beam like this. Now here's the thing, I cannot draw this without totally messing up my drawing. But if you can visualize a plate on the top and a plate on the bottom, that is an electric field that's moving the beam around. If you can visualize another electromagnet, which is here, and then it wraps around to the other side. So there's electrical plates, which are using the electric field to steer the beam. And then perpendicular to that, you have kind of a bar magnet going all the way around, but it's an electromagnet that you can also change the intensity of. So you can change the intensity of the charged plates to steer the beam, and you can construct this magnetic field also to steer the beam, and you can get those two to exactly cancel each other. So what you can do is you can say, all right, I'm going to turn these plates on and get the beam to slant up and hit the screen right here. And then I have these magnets, which I can also adjust, and I'm going to turn the magnetic field exactly to bring the beam back down and make it go straight again. So because you know how much you've deflected it, and you can measure that, and then you can adjust the magnetic field to exactly counteract that and make it go straight again, then you have all the information when you do a bunch of runs of this experiment to figure out how much charge must exist on this electron, right? Because that's what you're trying to do. They didn't really know what the charge actually was on the electron, and so they wanted to do these experiments. Now, it turns out that you don't have enough information to figure out exactly the absolute charge on the electron, but what you can calculate is the charge on the electron divided by its mass, the charge to mass ratio. So when you do these experiments, adjusting different electric fields and canceling them by the magnetic field, and you know how the strengths of all these things that you need to set up to get the beam to go straight, what you figure out is that for an electron, you have 1.76 times 10 to the positive 8 coulombs, I'll talk about this in a second, per gram. Now, the coulomb is something we haven't talked about. That's a unit in physics and also in chemistry. It's the unit, the SI unit of charge, of any kind of charge. All right, it's a very, 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 this is a very, very small, or I shouldn't say small. It's a unit that we use to talk about the charge of the electron, the charge of the proton, the charge of ions. It's something that you're going to get used to using as we go on. For now, I know we haven't done any calculations with coulombs yet. But for now, just know that when you do this experiment, you can calculate 1.76 times 10 to the 8 coulombs per gram of the electron. So you don't know the charge in the electron. What you know is the charge on the electron divided by whatever its mass must be. So ideally, you want to know what is the charge of the electron and what is the mass of an electron. This kind of bakes them all into one unit. It's that many coulombs of charge per gram of the electron, but we don't know exactly how many grams an electron is. So it sat like that for a while. And then several years later, because this is right at the turn of the century, the turn of the 1900s, right? So we started to understand how much charge per unit mass an electron, a single electron, would have. Then in 1909, a famous experiment called the Millikan oil drop experiment was conducted. And that purpose of that experiment was to determine the exact charge on the electron, right? To see if you could figure out what is that charge on the electron. Because everybody knew now that, this cathode rays were electrons. We want to learn as much as we can about them. Probably the most important thing we can understand is what is the charge. So a clever experiment using drops of oil was constructed. So I'll try to do my best. It's not going to be perfect, but basically here is like a drum. And I'll kind of come down here and draw it like this. And honestly, when I look at how he set this experiment up, I'm kind of in awe that somebody would even conceive of this, and then to be able to have the precision necessary to do anything meaningful with it. And to do it in 1909, that's crazy to me. But this was done, right? People are ingenious, right? So what you do at the top here is you inject into the top of this vessel oil. I'm not exactly sure what type of oil he used, but you can inject oil into the very top and spray it into very small droplets. So then the way this thing was constructed is there was a plate right here at the top, like this, with a hole in it right here. And so you inject this oil in the top and you inject it in a very fine mist, like very small I'm not talking about giant droplets or globules of oil. I'm talking about microscopic particles of oil, so small that you can't almost even see them. And what they do is they go, and of course there's this hole there, so they begin to kind of like go down kind of in a straight line through this hole, down towards another plate, which is located here at the bottom. I can do this, something like this, all right? Now these plates are charged because we know electrons are charged, and so we charge this plate up with a positive charge, and we charge this plate up with a negative charge, all right? Now oil by itself, yeah, everything has electrons inside of it, but because there's protons in the center of the nucleus and electrons on the outside, equal and opposite charges, most matter around you, including oil, doesn't have any observable charge from the outside world. It's kind of crazy that everything is consisting of these charged things, but we don't notice it because there's always equal and opposite amounts of protons and electrons, right? Same thing with the oil. So the oil is just this thing is coming down like this, but what they did is they then connected an X-ray machine and put X-rays into this vessel. The X-rays impact the oil, and when the X-rays hit the oil, they basically put a charge on the oil. or they force a net charge to happen on the oil droplets. The details of how that happen aren't that important, but basically what you can do is you can make the oil charged. So it's no longer a neutral atoms that are in there in the oil droplets. It's charged because it has a net charge on the oil droplets. Now, since the oil is microscopic and they now consist of having a charge on them, you can adjust the positive and negative terminal here to exactly, because the oil wants to fall down due to gravity, right? And you can then adjust the charge on the plates to exactly counteract the force of gravity. So everything wants to fall down. We know how things like to fall. Acceleration of gravity in Earth's gravity is a constant thing. So we know that the oil should take a certain amount of time, the tiny little drops, to reach the bottom. Now that they're charged, we can adjust the plates to exactly cause them to no longer fall anymore. And then we can know how or what the charge on the oil is. And from all this, I'm very much simplifying it. I mean, this is a crazy clever experiment to actually figure this out. Then it was figured out that the charge of a single electron must be equal to 1.602 times 10 to the negative 19, again in the unit, this is 602, sorry about that. The unit of coulombs, which is the unit of electric charge. Now I'm skipping over a lot of stuff because, I mean, there's just a lot of details in an experiment like this that, of course, he did back in the day. It's not so simple like there's a digital readout and it says, here's the charge. It doesn't work like that. What you do is many runs, and you figure out that the charge on the drops is always a multiple. The charge on these large drops, which are much larger than an atom, is always a multiple of this number. So because the charge is never smaller than this, and it's always a multiple of this number, then we deduce that one of these little electrons must have this as a unit of charge, because this is the common multiple. I mean, when you excite an oil droplet like that with an X-ray, it's not going to pick up like one electron. It's going to have some multiple electrons that are either knocked away from it or added to it, right? And it turns out that the multiple is always a multiple of this number. So they deduce this must be the charge on a single electron. Now here is where it gets, in my opinion, really awesome. Because before, from a totally different experiment, when we accelerate a beam of electrons and we can deflect them with a charged plate, and then we can use magnets, which I didn't draw, to counteract that, then we can deduce that the charge per gram must be this. And then from this experiment, we now know what the charge of an electron is. And so by putting those two pieces of information together and the power of dimensional analysis, which I've been telling you is like so important, you can calculate actually what the mass of an electron is. And we're going to do it right over here. If you start off by knowing the number I just wrote down, 1.602 times 10 to the negative 19 coulombs. This is the charge. I exactly wrote it down from the Millikan oil experiment, right? And then we go over here and say, all right, what else do we have here? We know that the electron is also 1.76 times 10 to the 8 coulombs per gram. We want to write it like this, 1.76 times 10 to the 8 coulombs per gram. Remember, anything in a unit conversion, you can flip it over either way. It's coulombs per gram. You can write it coulombs on the top and grams on the bottom, or coulombs on the bottom and grams on the top. We're writing it like this because coulombs cancel with coulombs. And the only unit we have left is grams. This is the power of unit conversion. So when you take this number, which is a tiny number, don't forget, and divide it by a really big number, what do you actually get? 9.10 times 10 to the negative 28, and this is grams. Now this was a value calculated in the early 1900s, right? Now, what about modern values? Right? The electron mass, the modern accepted value for it is 9.10938 times 10 to the negative 31, but the unit we use typically in calculations is kilograms. Notice what he calculated was 9.1 times 10 to the minus 28 grams, but if you want to take grams to kilograms, you need to divide by 1,000. So that's going to make this 3. It's going to be subtracting 3 from the exponent because you're going to move the decimal 3 spots to the left. That's why it's negative 31 kilograms. And then the electron charge, right, is the accepted value is 1.60218 times 10 to the negative 19 coulombs. And so look at these numbers, 1.60218, 10 to the minus 19. And what did we calculate for that? it was just 1.602 10 to the minus 19. So that's bang on exact to this many decimals. And the mass was 9.10938. We got 9.10. So we just have more decimal places now because we have much more sensitive experiments than dropping droplets of oil in a container. But just take a step back, okay, and realize that prior to the turn of the century, prior to the turn of the 1800s into the 1900s, no one on the face of this planet knew that an electron was a thing. Nobody. Think about that for a minute. It's only been about, the year of this recording is 2022. I hope people are watching it for many, many years in the future. So right now, as of the time of this recording, it's about 122 years since, and maybe even less than that, because this was discovered in like 1909? Yeah, 1909, right? So about 110 years. Nobody knew what an electron was or that it even existed before these experiments. But we have gone from knowing now that electrons exist to, we'll talk in the next lesson, that protons and neutrons also exist, to knowing how chemistry exists, how to control chemistry to build things that can help our lives and to enrich our civilization, to making rocket engines and solar panels and computers and cell phones, all of that stuff happening in a span of about 100 years. Right? It's incredibly crazy that we were able to do this, that the collective minds of all these people have done this stuff. And here I am talking into a camera to pass this information to you, right? So this was a conceptual understanding of the discovery of the electron. It's helpful in the beginning to think of it as a little ball, okay? So yes, think about it. But in the back of your mind, just remember that there will come a time in the future when I tell you that that is wrong and that it's not a little ball. An electron is really a little wave. That is the punchline. It's a little wave. You have a bunch of questions now. What do you mean a little wave? What's waving? Okay, what's moving? In water waves, the water moves, right? For light waves, we say electric and magnetic fields are waving. What's waving for an electron? Why is an electron made of a wave? Great questions. I hope you can figure out the answers because we don't actually know the answers to a lot of these questions. But we know that an electron is not a little solid ball of like a bullet or something. It is a wave. And I'll give you a little bit of a preview when we get down the road. Much later when I do a more of a lesson on introductory quantum mechanics. Basically, when we shoot waves, actual waves, like either water waves or even light waves, at two slits, the light waves and the water waves, they interfere with each other. That means the crests and the troughs, they line up and they either add to get bigger or they subtract to cancel each other out, because waves, when they collide like this, after they go through a pair of slits, they interfere and they add and subtract, and we can see the interference. We know exactly how that happens. We have all the math, we know how all of that happens. But it turns out when you shoot electrons at a pair of slits like this, they don't behave like little bullets that just go through the slits. They actually interfere with each other, and we see an interference pattern on the other side of the slits when we shoot electrons. Even if we only shoot one electron, we still see an interference pattern on the other side. So we know that there's some kind of wave character to electrons, and we know now from quantum mechanics that every piece of matter around you has some kind of wave character. Everything around you is basically made of waves. Now, what is waving? Why is it waving? How fast is it waving? Those are all things for a different lesson on a different day. Here, we're just learning how do we discover what an electron was, and how and what the charge and the mass of an electron is. And that we could use these experiments to get pretty close to modern day values. As we go through chemistry, you're gonna know and realize that everything chemically is happening because of electron transfer or electron sharing. And then when we get farther into it, of course, I'll drop a bomb on you and tell you that an electron isn't a little ball at all that's orbiting, it's a wave. And all of our modern theories support that with very, very accurate experiments. The best experiments we can do. So for now, watch this, make sure you understand how we have discovered what the electron is. Follow me on to the next lesson. We'll talk about how the structure of the atom was actually deduced, and we'll learn about the protons and the neutrons, of course, which are in the center of the atom.